All right, welcome back. Second day of hypothesis test notes. We're going to talk about more about the hypotheses, null and alternative hypotheses, and then type 1, type 2 errors that we can make as well. I do want to first start by going over some answers to the check your understanding on the previous page. So calcium is a vital nutrient, and we said that the NIH recommends a calcium intake of 1,300 milligrams per day for teenagers. The NIH is concerned that teenagers are not getting enough calcium on average. Is that true? So our hypotheses, our null hypotheses, is kind of what was first stated there by the NIH, is that the mean, the average, the true mean, mu, is 1,300. And alternatively, that the mean that teens are taking of calcium daily is less than 1,300. So that's our null or alternative hypothesis. They decide to perform a hypothesis. They ask a random sample of 20 teens to record their food and drink consumption for a day. They compute the calcium intake for each student. The sample mean, X bar, is 1198, and the sample standard deviation is 411. They perform a significance test and obtain a p-value of 0.1404, so about 14%. We're going to start performing these significance tests very soon. We're just talking about what they mean right now. So what does the null hypothesis, what does it mean for the null hypothesis to be true in this setting? So if the null hypothesis, or mu equals 1,300, is true, that means the mean daily calcium intake in the population of teens is indeed 1,300 milligram. The p-value here of 0.1404, what does that mean? So assuming that this null hypothesis is true, that the mean daily intake is 1,300, that the null hypothesis is true, there is a 0.1404 probability of getting a sample mean of that 1,198 milligrams or less purely by chance. So we're saying, like, how often, if this 1,300 was true, that teens were actually getting 1,300 milligrams of calcium a day, how often, when we took a random sample, would we get 1198 or less? And it would happen about 14% of the time. So based on this alpha here at a 0.05 level, remember our alpha, as we go up here, is our significance level. And that's kind of what we compare our p-value to. And so where are we at here? Because that p-value is greater than the alpha level, we will say we fail to reject the null hypothesis, and that we do not have convincing evidence that the mean being 1,300 milligrams is not true. So we can't say that we don't. If we got something like 1% of time, we would actually end up with this 1198 or less, or like close to 0% of the time. Then we say, all right, something's weird that we got this number or lower than this number, and we should really say this is significant evidence against the mean being 1,300. We will get there probably next class, not this class. This class, we are talking more about hypotheses and type 1 and 2 errors. So the Wolverine Worldwide, a shoe company in Rockford, I believe this is still in Michigan. You can go research this and Google Wolverine Worldwide disposal of chemicals, which have leaked into the groundwater. So you may have heard before about Michigan and groundwater and their water, and that it's not safe to drink. We had some not safe to drink water here a week ago. The state's drinking water limit of 70 parts per trillion, or PPT, is considered safe. Anything above that is considered dangerous. So officials believe the water in Rockford may be unsafe. So they take a random sample of 200 households in Rockford, and they found the average lead level of the sample is that 70.5 parts per trillion, which, is kind of close. So we're going to figure out if that's meaningfully close or not. So we need to start with our hypotheses. Our null, let me zoom in here a little bit and make this a little bit bigger for everyone to read. Our null hypothesis, H sub 0, is going to be, and we want an equal sign here. We got to figure out what we're talking about. We're talking about, it seems like, an average. The average, there we go, average lead level right there Let's highlight that real quick. The average lead level. So that tells us that we are talking about mean. So let's get our little equation here. And we want that the mean is equal to 70 parts per trillion. And if that is true, then that would tell us that the water is safe. Alternatively, our alternative hypothesis, which we call H sub A, is not that the mean is equal to, but we're really more worried about the mean being greater than 70 parts per trillion, because then that is considered dangerous, as we can see here. Anything above 70 parts per trillion is considered dangerous. So that's our alternative hypothesis. If this is true, then the water is unsafe. I believe we also need to throw down here that typically we have a significance level alpha of 0.05 or 5%. After conducting that significance test, they find this p-value. Notice how that p-value is compared to our alpha level. And let's interpret what that means. So assuming that the null hypothesis is true, so that the water is safe, the null hypothesis is true, that mu equals 70 parts per trillion, there is a 0.045 probability of getting a sample mean of 70.5 parts per trillion or more purely by chance. Let me get rid of that purely, and hopefully we can have that all there together. So if this is true, that's not how I wanted that to go. Here we go. That was weird. So if this null hypothesis is true, that the mu does equal 70 parts per trillion, then there is about a 4.5% chance of actually getting a sample mean of what they got, the 70.5 parts per trillion or more. So that's kind of low. That won't happen that often. Then that means that we should probably reject the null hypothesis and say that we have evidence for the alternative hypothesis. So let's compare that. Since that 0.045 is less than 0.05, then we should reject the null hypothesis and recommend that the city switch to bottled water, since we have convincing evidence for the alternative hypothesis. And we'll see if I spelled alternative right in a second. A little smaller. That was bigger. Smaller be there. So important things here: reject the null hypothesis, since we have that convincing evidence, and we show that comparison there of our p-value compared to our alpha value. So now we got to talk about errors. So let's suppose that this decision is wrong. What would be a consequence of this error? So if they go and they say, hey, drinking water is not good, please drink bottled water, but the water was actually okay, they would just waste money and resources on bottled water. Okay. This is what we call a type 1 error, where the null hypothesis is true, but we reject the null hypothesis. So how often will this error occur? And it'll occur based on our significance level. So since our significance level is that 0.05, then this is going to occur that often. So 5% of the time we get statistically, there we go, significant results purely by chance. Type 1 error occurs the same percent as the significance level alpha. Let's make sure we can read all that. In this case, our alpha level is that 5%. All right, so number 6 says, suppose the p-value was 0.14. Should the town keep the current water or switch to bottled water? So because that 0.14 is greater than the significance level 0.05, the town should keep the current water since they don't have convincing evidence against the null hypothesis. So in this case, we would fail to reject the null hypothesis. Well, what if that's wrong? What's the consequence of this error? So if this is wrong, we say, hey, don't worry about it. You guys can drink your water. You'll be fine. And people actually drink the water, then they're drinking unsafe water and could possibly get sick and die. So this type of error is a type 2 error, where the alternative hypothesis is true, but we fail to reject the null hypothesis. So what we're going to do in a little bit is you're going to start a study. You're going to come up with a concept, and you're going to figure out the hypotheses. You're going to figure out what a type 1, type 2 error is, and then the final step is going to be which error is going to be worse. So in this case, our two errors are number 4 and number 7. So number 4, we have a type 1 error where our null hypothesis ends up being true, but we reject it. So in this scenario, they waste money and resources because they switch to bottled water. Versus number 7 here, we have a type 2 error where our alternative hypothesis is true, that the water is unsafe, but we say we don't reject the null hypothesis and say, go ahead and drink that water. So hopefully we can determine that the consequences in question 7 are more serious because people getting sick and dying seems worse than wasting money and resources on buying extra bottles of water. So we can jot that down here. Saying that number 7 is more serious consequences. It has more serious consequences. People would get very sick, which is worse than wasting money. So we'll wrap up this lesson by writing out our type 1 and type 2 errors. And we'll go find a nice little diagram to show that as well. So type 1 error. The null hypothesis is true, but we make the wrong decision. This occurs by a chance of alpha percentage. So percent symbol, and let's go get the alpha symbol here in the equation here. Nice little alpha symbol. We can put it right next to the percentage button. There we go. And that's versus a type 2 error. We're going to make this red. And that's the alternative hypothesis is true, but we make the wrong decision. So a fun little image here that I found just by Googling type 1 versus type 2 error to get you an idea here. Let me try and paste that. Okay, let me go try that again. 1 second. All right, so here's a image here showing type 1 versus type 2 errors. So type 1 error, false positive, where the null hypothesis would be that he's not pregnant, but we make the wrong decision and say that he is pregnant. Versus a type 2 error where the alternative is true. So if our null hypothesis is that you're not pregnant, but clearly we can see that she is pregnant there. So we'll wrap up with this diagram here, where if we have true and true, we're right. We have false and false, we're right, with our measured or perceived what we say happens versus the reality. So if the null hypothesis is true, but we make the wrong decision, we have a type 1 error that's a false positive. Versus type 2 error if the alternative hypothesis is true, so false, but we say that in reality we make the wrong decision and it ends up being true, we have a false negative there. So you guys will create your own type 1, type 2 error concepts and post that. Look for Canvas. See ya.